Hi everyone, my name is Chelsea Finn and I'm an assistant professor at Stanford and I'll be talking about self-supervised robot learning. So to start, I'd like to actually start a little bit with a story. When I was starting my PhD, I worked a lot on reinforcement learning and how we might enable robots to learn through trial and error. For example, here you can see the robot learning to place the red block into the shape sorting cube. And at the beginning, it knew very little about how to do the task. And over time, it's getting better and better at kind of getting it closer to the correct matching hole. And at the end, it's able to actually figure out how to successfully place it into the hole. And the final policy that you get looks something like this, where you can see the robot's visual inputs right here. Now, this seems like a very sensible way to train robots to solve tasks. And one of the things that's exciting about this kind of approach is that you can allow the robot to solve not just one problem, but to solve many different tasks. So the robot can use trial and error to learn how to place the claw of a toy hammer underneath a nail, to screw a cap onto a bottle, and also in kind of some follow-up research, learn how to use a spatula to lift an object into a bowl. Now, this seems like a very sensible way to train robots, and other works have used this same sort of reinforcement learning technique to train robots how to hit a puck into a goal, how to open a door, how to throw an object to hit a target. And around the same time, a lot of other research on playing games and locomotion has used these same sorts of techniques to develop behaviors for other kinds of problems. Now, well, in many ways, this is a sensible approach, like I've mentioned, for training robots. We have a bit of a problem. And the problem is that the robots here aren't learning general behaviors like how to throw objects and how to manipulate objects. What the robot is learning here is, for example, how to use this spatula to lift that object into that bowl. And if you gave it a different spatula or a different bowl or change the scene in some way, the robot wouldn't be able to solve the task because all of the data that it's seen is from this particular environment. So the robots here are learning one task in one environment starting from scratch. And if, for example, we want the robot to solve other spatulas, then it needs a much broader experience in order to be able to handle not just one spatula, one environment, and not just one task. It needs lots of data and lots of more diverse experiences than this one single task in this one environment. And in some ways, you can think of this analogously as on day one, giving an infant a spatula and training them just to do the task of using that spatula to lift objects. And from this standpoint, it's actually quite silly that that we would actually train robots in this way. At least if we care about developing robots to do a wide variety of behaviors in a wide variety of environments. So can we build more general robot learning systems? Well, we can take some inspiration from what people do. Like I mentioned, people don't start training for one task on day one. We instead accumulate and learn from broad experiences, like the baby shown here. And perhaps if we can allow robots to learn from these kinds of very broad experiences, then they might be able to solve a wider variety of tasks and operate in a wider variety of environments. And in many ways, that'll be the topic of this talk. And I guess it's worth mentioning that AI has solved a lot of really impressive things ranging from Jeopardy to becoming the grand champion of Go, to helicopter acrobatics, to machine translation. And some of these are also really useful and undoubtedly difficult things to do. However, you might wonder, like, why haven't we solved these really basic yet general object manipulation skills, motor control skills? And it turns out that the simple yet general manipulation skills are beyond the scope of current AI methods, and even manipulating Go pieces in a general and wide range of setups is an unsolved problem. How is this the case? Well, it turns out that these simpler and broader capabilities, the things that are the most intuitive to us as humans, are actually the hardest to reproduce in machines, in some ways because we don't know exactly how we do it. It's so intuitive to us. and it's something that we learn at a very early age. And this is known as Moravec's paradox. So in this lecture, I want to talk about self-supervised robot learning and moving towards kind of methods that allow us to get more general motor skill capabilities. Okay, so how does this differ from problems like object classification and ImageNet? Well, in object classification, it's a supervised learning problem where you can collect input-output pairs. You can collect images and their corresponding label as data. This data is IID, or independently and identically distributed. This means that the train and test data is kind of from the same distribution, and you don't have to worry too much about challenging correlations in your data. You can also collect a very large and labeled and curated data set using data from the internet. And there's also a well-defined notion of success. If you're very accurate at predicting the correct label, that means that you're doing a good job. Now, in object manipulation, things are quite different. So this isn't just a problem of outputting the correct label, it's actually a sequential decision-making problem where you need to actually produce the right action or produce the right decision at every point in time, and essentially your action will affect the next state of the world that you're in. And this means that if you make some errors early on, those errors will compound and lead to states that are very different from what you saw before. Also, it's unlike massive amounts of the internet or data on the internet, it's not clear how we should go about collecting data or even what the labels should be, what the inputs and the outputs should be. And then finally, it's also not clear exactly what success means. We would like robots to perform useful tasks for us, but we don't have a very clean metric that we can optimize and then get the right behavior or get good and intelligent behavior out. So for this reason, these kinds of problems actually tend to be much more difficult than supervised object classification or language classification or speech recognition and so forth. Okay, so how do we go about approaching this problem? So I'll outline kind of one approach for doing this that allows us to move much more towards broad data and broad sets of skills. So to start, we need to collect some data, and we're going to start by collecting data that looks like this. This is just data that was actually collected by randomly commanding the robot to do different actions, such as opening and closing the gripper, moving the gripper up and down and left and right, and so forth. Essentially, the robot is almost playing here in some ways, although it's kind of a scripted behavior. And in contrast to the videos that I showed before, in this data, there's no notion of progress or success for solving a particular task. But that's perhaps a good thing, because we do want to learn not something for one particular task, but we want to learn something more general about the world. But of course, then this gives us the question of how should we learn from this data? So once we have our data, what we're going to do is we're going to try to use it in a self-supervised way where the data is going to supervise, the data itself is going to supervise what we're learning. And in particular, what we're going to do is we're going to learn how to predict the future. We're going to try to learn models that look like this, where we can predict what will happen if the robot commands its arm in different ways. So for example, if it commands its arm over here, it should predict that the objects will kind of move over to the left, and maybe there's some blur because the robot is somewhat uncertain or fuzzy about exactly what will happen. And in contrast to the very directed reinforcement learning approaches that I was talking about before, these approaches capture much more general purpose knowledge about the world. They can capture things like objects and physics. They use all of the available supervision signal in this data. And they also don't have any assumptions about task representations. So for example, if you wanted a robot to fold a towel, you don't need to have some sort of computational representation of a towel to solve this task. And this is because it's trying to predict directly in its observation space. It's trying to predict what the future will look like based on the actions the robot takes. And then lastly, one of the things that's nice about this sort of self-supervised prediction problem is that it is inherently a supervised learning problem, because we have kind of labels, we have data of what the future looks like in our data. And so this means that we can scale our models and get better and better predictions. So for example, a model from a couple, actually fairly recently, from a couple years ago, scaled these video prediction models and got predictions that look like these below. And you can see that the predictions actually look quite realistic and also are close to the ground truth. Okay, so how do we actually go about predicting these videos? Essentially, it corresponds to a deep neural network trained with supervised learning, where we're trying to take as input an image, take as input an action that the robot took, like commanded positions of the joints, for example, and then train the model to generate the next image. And so we essentially, like, this is our input X, this is our output Y, and we're just training the network with supervised learning to solve this prediction problem. And I don't want to go into too much of the details of the kind of intricacies of these kinds of architectures, but you can think of these architectures as these recurrent neural networks because they're trying to predict not just the next image, but a sequence of images. And further, there are convolutions because we're dealing with image data. And importantly, it takes as input an image, it takes as input an action and maybe some information about the robot's arm state, and is predicting the next image. Okay, so we have these now kind of self-supervised models of the world, of the future. The next question is, how do we actually use these models in a useful way to solve tasks? And this is where we need to actually try to figure out how to solve goals, and we need to also accept some sort of task specification from a person. And so the way this is going to work is we're actually going to, now that the robot can kind of foresee the future for different actions, we're actually going to plan. We're going to try to figure out what actions will lead to the future that I would like. Okay, so the way this works is, say this is the robot's current image taken from its camera. We're going to consider a large number of potential action sequences. So for example, we might consider these two action sequences. We then predict the future for all of the action sequences that we're considering. And so, for example, here might be the two predictions for these two actions, and you do this for all of the considered action sequences. And then you take the video prediction that matches the future that the robot wants to achieve and execute the corresponding actions. And then you can also kind of iteratively kind of rerun this process at each time step and replan just in case something unexpected happens or just in case some disturbance happened in the environment. Okay, so the kind of fancy name for this is visual model predictive control, or visual MPC, where model predictive control is just saying that we are kind of iteratively planning actions using our model of the world. So there's a couple more questions that arise, and actually kind of getting into the details of how you actually do this. One question is, what future is the best future? How does the robot choose what the best plan is? And this is a question of how we can specify tasks to the robot. And we've experimented with a number of different ways to do this, and in general, there isn't any one answer. But for example, the human could specify a goal by selecting where they want pixels to move. So if you want the robot to put the apple onto the plate, you can kind of specify the pixel on the apple and specify a pixel on the plate and say, I want the object corresponding to this pixel to move over here. You can also specify a goal by providing an image of what future you want the robot to get to. And you can also provide a few images, example images of success, and use this to learn a classifier that tells you whether or not the future or whether or not an image is desirable or not desirable. Okay, and then the way that this works is then a human specifies the goal. Then the robot uses its learned model of the world to plan with respect to that particular goal. For example, to try to reach this, this goal of moving this pixel over here. And then you actually run those actions on the robot, and the robot will then, in this case, approximately fold the leg of this pant. Another example is you can give a few examples of success, and then, for example, of telling it that it should put the pencil case behind the notebook, in for a classifier of what is good and what is not desirable, and then run planning with respect to this classifier. And then, of course, run the actions on the robot to get the robot to solve the task. Okay, so to recap, the way that this algorithm works is you first run some policy, for example, a random policy to collect data in the robot's environment. Then learn a model, learn how to predict the future based on all of the data that you collected. Then use this model to plan a sequence of actions that accomplishes some desired task. And then execute the first planned action and observe the resulting state. And then you probably want to append this to your data set, and then kind of go back to your first step of optimizing your plan and kind of replanning and re-optimizing for your actions. And of course, at the second step, you can actually warm start this optimization or this planning process based on the plan that you had at the previous time step. And then if you're kind of collecting a lot of data in this process, you can also go back and use this to update your model and learn a better model based off of all your most recent experience. Okay, so that's the gist of this self-supervised robot learning approach. And one of the things that's really cool about this kind of approach is that instead of getting the robot to solve just one task, like putting the block into the shape sorting cube, the robot can actually use this video prediction model to solve a wide range of tasks. So for example, if you tell it to pick up this plush toy, it can figure out how to do that. If you tell it to move the sleeve of this shirt over here, it can figure out the actions of its robot arm that will accomplish that task. It can also do the task of placing an apple onto a plate, like I mentioned before. And it could also solve a range of other tasks of simple manipulation skills like folding the pant leg that we saw before, moving an object over here, and covering an object with a towel. And all of these skills were learned without any sort of supervision, just essentially by sort of like playing with objects in its environment, learning a model, learning how to predict the future, and using that model to plan. Okay, so now there's some remaining questions, and I want to dig a little bit into some of the frontiers and some of the kind of more recent work in this area. So first, you might ask, why is the robot slow? The videos on the previous slide were sped up 2x, and even then, the robot was still moving somewhat slowly. You could also ask, can we scale these models to even broader data, not just to a single environment, but to many environments? And also, instead of having it be entirely self-supervised and self-learned, can humans play a role in the process? So first, in terms of the question of why the robot is slow, the reason why it's slow is because it's optimizing for plans at test time to solve the task. And one thing that you can do instead is learn this policy, essentially compile this planning process into a model that predicts the action given the state, predicts what to do given the image. And if you do this sort of offline optimization of a policy ahead of time for a particular task, rather than trying to do all of that sort of planning process at test time, then you can actually get a policy that moves a lot faster. So this is a policy that is trained for the task of closing the drawer. And this is a video in real time. And you see that the robot moves more smoothly and faster. And this policy also has a 76% success rate. Okay, so that's one way to speed up the robot. What about scaling these models to broader data sets? So in the data sets that we were looking at before, it was actually a single robot in a single environment, but with lots of different objects. What about scaling to a much broader data set where there are, in this case, there are 7 different robots, lots of different viewpoints and environments? It turns out that if you apply these sorts of video prediction models, even the pretty recent models from a couple years ago to this data set, they aren't very good at predicting the future. So for example, here it isn't able to capture the robot's arm even. And it turns out that these predictions are actually representative of predictions on the training set. So it isn't even able to capture the training data. And so here kind of the bottleneck in handling these more diverse data sets is a problem of underfitting and not being able to fit the training data. So how can we try to scale dynamics models? One thought is that we could potentially learn to only model the things that might matter for a set of tasks. And there's a few different ways that we could do this. One would be to learn a representation of your image, a lower dimensional representation of the image using some sort of task supervision. So for example, you could try to have an input image and predict kind of the positions and orientations of objects. And there's also an approach called Planet that also learns a representation using actually reward supervision. And this approach can actually work quite well if you can get a lot of supervision of like all the objects in the scene and a lot of supervision on what parts of the image matter and what parts of the image might not matter for a task. The downside though is this does require a significant amount of supervision per task that you want to solve. So for example, if one of your tasks is to manipulate this box of Cheez-Its, then you need to have a lot of supervision telling it to basically training a model to recognize the position and orientation of the Cheez-It box. So this isn't something that isn't quite as scalable as we would hope. We also have some more recent research on trying to learn representations that are tailored to a provided goal image. And this doesn't require any supervision, and it can actually successfully redistribute model errors in certain ways and try to be more accurate on parts of the image that are important and less accurate on the things that don't matter. But this is also really kind of on the frontier of research, and we really need more research to figure out if this is a viable approach. So this is one idea for scaling models, is maybe instead of trying to model everything, we can try to only model part of the image. Another approach is to try to actually just make the models larger. And actually one practical bottleneck if we do this is we run into the limits of the memory of our GPU. And to solve this problem, we can actually rely on an old trend of layer-wise training of neural networks. This was actually something that was quite common in kind of between 2006, 2010, and so forth. And the way that this works is you essentially train a one-layer neural network, one-layer autoencoder to generate, to essentially just generate the future or generate the current input with just a single hidden layer. And then once you train this first layer, then you can train the second layer of the network to reconstruct the activations of that first layer, and so on and so forth. And this approach first reduces memory costs because you don't need to necessarily store all of the forward and backward passes of these weights and activations. And it also actually leads to somewhat of a curriculum. It makes training a bit easier. And that's actually why, one of the big reasons why these prior approaches used them. And so what we can do is we can actually take this idea that was from quite a long time ago and actually use it to train video prediction models, where we first train kind of a one-layer neural network to predict the next frame, and then freeze this first layer and train the second layer to predict the next frame, and so on and so forth. And so kind of the high-level bits of this model is that we're going to be training each of these modules sequentially, one at a time. We're optimizing each with respect to the evidence lower bound, which is trying to kind of essentially maximize a lower bound on the likelihood of the next frame. And the reason why we get big memory savings is we no longer have to compute anything in the kind of the backward pass of this part of the network. And then another important detail is that we're actually going to be compressing the spatial dimensions of the image as we encode and go deeper and deeper. And the reason why we want to do this is to prevent correlations in our latent variable model. And this is because we're using a technique called variational autoencoders, which assume that basically assumes that each dimension of this latent space is independent. This is called the mean field approximation in variational autoencoders. And if we're making this assumption that each dimension is independent, then we should try to avoid the fact that kind of compress it into a representation where we don't have like correlations between neighboring pixels. Okay, so we can take these models, and because they're much more memory efficient in terms of training, we can actually train larger models. And so what we did is we trained a much larger model that could still fit in the same amount of GPU memory on the RoboNet dataset that I mentioned before, and then fine-tuned it on a small amount of data from this particular robot domain. And what we found is we then kind of tried to have the model be used to plan for a number of different tasks. It looks like this left video isn't playing, but for example, we would give it a goal image of trying to sweep this milk carton off of the plate, and then we see that the robot can successfully perform that task. And on both kind of these sort of sweeping or picking and wiping and picking and sweeping tasks, we see that even with unseen objects, we see kind of a 90 or 87.5 success rate of this larger model compared to a 50% success rate of the model that is smaller. Cool, so we can essentially scale these models to broader data by trying to fit kind of more juice and increasing the size of the models without needing to increase the size of our GPUs. Okay, then the last question is, how can humans help in this process? So everything so far has been completely self-supervised with data collected autonomously by the robot. However, we could imagine providing some guidance and showing the robot interesting behaviors, such as demonstrating how to use a tool in this circumstance. And if we have some of these diverse demonstrations of showing kind of more complex behaviors to the robot, what we can do is we can use this to improve each step of our process. So we can first use this data in conjunction with the data that it collected before to improve its predictive model. And then we can also fit essentially a model of human behavior to the demonstration data and use this to direct the data collection process to collect more data like the way that humans collect data, and also to guide the planning process to consider not just all sorts of action sequences, but also to consider particularly the action sequences that fit within the model of the human behavior. And so we consider this in the context of a kind of a tool use domain where we want the robot to learn how to pick up and use a tool in different ways. And we can see some samples of the behavior model, the human behavior model here. And what we find is that we can solve more complex tasks with this. So the way that it works again is we specify a goal by specifying where we want objects to move in the image. We then run planning process using the robot's predictive model of the future, guided by its model of human behavior. And then we run these actions on the robot to get the robot to actually solve the task in the real world. And by using this sort of human data, the robot can not only still solve a variety of tasks, but it can solve more complex tasks where it needs to pick up an object and use an object to solve the task. This also includes things like bringing this blue object closer to the robot when the robot is constrained to move in this green region, and it needs to figure out that it should pick up the hook and use that to bring the object closer to itself. It can use objects like sponges that it hasn't seen before to solve a task, or objects like a water bottle as a tool to sweep objects over to the side. And it can also decide when to use a tool, for example, when there are two objects that need to be swept over versus when it isn't necessary to use a tool and it can just move the object directly. Okay, so the takeaways here are that of the entire lecture is, first, if we want robots to generalize broadly, we should not train them for one task in one environment, but train them with broad data. And this yields this kind of encourages us to look at self-supervised learning on this broad unlabeled data. And the way that we can do this is through this two-step process where we train a generative model of the future and use this to solve tasks via planning in the model. And then lastly, we talked a little bit about some of the frontiers, such as offline policy optimization, scaling to larger models, and incorporating human guidance. And yeah, I'd like to thank also a lot of the students who played a role in a lot of the work that I presented.